speaker. So it is Professor Wang. She's a full professor at both the Courant Institute in New York and also since this year at the IAGS in Paris. And this is quite remarkable since Hong only defended her PhD at MIT in 2019. And Hong has so far received the Mariam Mirzakhani New Frontiers Prize in 2022 and the Salem Prize last year. And these prizes have been awarded for Hong's many beautiful results in Fourier analysis and in geometric measure theory. Her results are the current world records in most of the key problems in both fields, such as Stein's restriction conjecture and Faulkner's distance set conjecture, and the Furstenberg set problem. Most recently, in a series of 3 landmark papers with Josh Zahl, which culminated this spring, Hong solved the 3-dimensional case of the Kakeya set conjecture. And this is what Hong will tell us about today. So please, Hong.
Thank you very much, Thomas, for the introduction, and thanks very much for the invitation. It's a great honor to give the Finnish colloquium. I'm going to talk about Kakeya sets in R3. So here is the definition. A Kakeya set in Rn is a compact subset containing a unit line segment in every direction. So one simple example is the unit ball that contains a unit line segment in every direction. And then this is a more sophisticated example. As you can see, the unit line segments can rotate, so it can put pointing in every direction. And if you calculate, this area is smaller than the area of the unit ball or the unit disk. And the question is, how small can a Kakeya set be? It's surprisingly, Besekovich constructed in 1919 a Kakeya set of 0 measure, which is the construction is as follows. So suppose we only focus on the unit line segment in this 60-degree sector, and where we can take an equilateral triangle, and then this contains all the unit line segments in this sector. And how can we make a set containing this line segment smaller? The idea is to cut the equilateral triangle into half and then move them closer. Since they overlap a lot, like this shape is repeated twice here and then only once here, so the area becomes smaller. You can iterate this idea, decompose the triangle into many small pieces, many smaller triangles, and then you move each pair of the triangles closer and then closer. This becomes very spiky picture. It's called a parent tree. And this process will give us Kakeya set of arbitrary small measure, so which is a big surprise. Now that we know the Kakeya set could have 0 measure, then how large or how small can the Kakeya set be? So there are many sets that could have 0 measure. To quantify the size of those sets, one can use the notion of Hausdorff dimension. So the Kakeya set conjecture states that any Kakeya set in Rn has Hausdorff dimension n, which means the Kakeya set could not be too small. It should have 4 Hausdorff dimension. So how do we think about Hausdorff dimension? Here is here is a heuristic that's not rigorous, but it serves as a nice intuition. So it says that when we try to imagine a set with Hausdorff dimension n, even though the set E could have 0 measure, how do we imagine it? So we are going to take delta to be a very small scale, and eventually we're going to let delta goes to 0. And then we take the delta neighborhood of the set, and we want the area or the volume of the set of its delta neighborhood to be greater than delta to the epsilon, where epsilon is positive and it goes to 0 as delta goes 0. It says that the volume of its delta neighborhood goes to 0 very slowly. So This is how this is a helpful way, although not rigorous way, to imagine a set of house dimension n. Why do we care about the Kakeya sets? It's I care about the Kakeya set because of its connection to Fourier analysis. So Fourier analysis is useful both in mathematics and also in real world. One of the fundamental formula is the Fourier inversion formula. It says that if we take the Fourier transform of f, and then we take the inverse Fourier transform, we recover our f. The Ball multiplier conjecture says that, well, when we take the Fourier transform and then take the inverse Fourier transform, if we lose some information, for example, if we only know its Fourier transform inside a large ball of radius r, then can we still recover the original function as the radius goes to infinity? So at the beginning, you might think that this is a very natural conjecture because this chi br is the indicator function of ball of radius r. Then as r goes to infinity, it converges to the identity function. So since this converge, then it's very natural to ask whether that this Ball multiplier is also converge. It's a big surprise when Charlie Featherman disproved this Ball multiplier conjecture for a large class of functions in the 1970s using Besickovich's construction. The key for Featherman's counter example is that there exists a zero measure Kakeya set. So this shows how Kakeya set is closely related to Fourier analysis and also closely related to how different wave overlap. So it's because of its connection, there has been many mathematicians working on the Kakeya set conjecture. So the dimension n was solved by Davis in 1970s, and then starting from dimension 3, the problem becomes very difficult. And there has been the work of Jean Bourgain, who proves that any Kakeya set in R3 should have Hausdorff dimension greater or equal than 2 plus 1/3, and also by Tom Wolf, who showed that any Kakeya set in Rn has Hausdorff dimension greater or equal than 2 plus 1/2. So these two results uses elementary and highly non-trivial method. The first one is called the Bush argument, and the second is called the hairbrush argument. And then starting from Wolf's result, to improve Wolf's result, one has to use modern mathematics. The work of Katzlaber and Tau, they showed that any Kakeya set in R3 should have Minkowski dimension, which is a weaker notion of dimension, greater or equal than 2 plus 1/2 plus a tiny positive number. This is a big breakthrough because, as we can see later, there is a theoretical barrier to improve Wolf's bound. And then joint with Josh, we showed that any Kakeya set in Rn has a Hausdorff dimension. Any Kakeya set in R3 has Hausdorff dimension 3. And the conjecture in dimension n greater or equal than 4 is still open. So why is this 2 plus 1/2 bound very hard to improve? While Katzlaber and Tau, they study the Kakeya set conjecture in Rn, and when they try to improve Wolf's bound, they discovered the following Heisenberg group example. So the Heisenberg group H is a subset of C3. That is the imaginary part of Z1 equals to the imaginary part of Z2 times the complex conjugate of Z3. This Heisenberg group contains 4 real dimensional family of complex lines. So the lines are parameterized by ST are real numbers and alpha is a complex number. then LST alpha, the line is this. One could calculate that it's indeed a complex line contained in the Heisenberg group. And since if we identify C3 with R6, then this becomes real hypersurface in R6. So the real dimension of the Heisenberg group is 5. So it equals to exactly 2 plus 1/2 times the dimension of complex numbers. So the Wolf's method is very general. It works equally well for the Heisenberg group, which contains a lot of complex lines, and the Kakeya sets. So this means that in order to improve this bound, one has to distinguish the Heisenberg group and the Kakeya set. And this is a very difficult problem. At the beginning, you might think that this Heisenberg group does not really contain a complex line in every complex dimension because this S is a real number, so it misses some directions. But it is very difficult to use the assumption that Kakeya set contains a line in every direction. This a line in every direction assumption, as we will see later, is very hard to use in the proof. So it turns out that the way the approach we use is to say that Heisenberg group exists in C3, but the Kakeya set exists in R3. We were able to distinguish the two examples by distinguishing the space they lie in, the spaces they lie in. In the work of Kaslab and Tao, they also discovered some of the key structure of some hypothetical counterexample to the Kakeya set conjecture. They say that they showed that if a Kakeya set has Minkowski dimension 2 plus 1/2, then it has to be sticky, grainy, and plany. We will see the notion of stickiness later in the argument. It plays a key role, and not only in the Kakeya set problem, but also in many other problems in geometric measure theory. And then later, Larry Guth showed that more generally, any hypothetical counterexample to the Kakeya set problem, not necessarily with this dimension, should have grainy property. So here is, I hope this is a very quick summary of the history of the Kakeya set problem. So to begin our analysis, previously we said that one way to imagine Hausdorff dimension is about taking delta neighborhood of the Kakeya set. Then since the Kakeya set contains a line in every direction, when we take the delta neighborhood of a line, it becomes a delta tube. So it's useful to consider the following discretized problem. So let delta be a small scale, and the delta tube is just delta neighborhood of a unit line segment. The Kakeya assumption in the discretized setting says the following: a set of tubes, blackboard T, consists of a delta tube in every delta separated direction. So what does it mean is that on the unit sphere, we take a delta net. So it means that at a point and its neighbor has a distance roughly delta. And for each direction in this delta net, we take a delta tube in the direction. So the delta tube, we can translate it, but it has to be one in every delta separated direction. Then the Kakeya set conjecture says that the discretized Kakeya set conjecture says that if a set of delta tubes satisfies the Kakeya assumption, then the volume of their union is greater approximate than 1. So this note this notation means greater than delta to the epsilon, and epsilon goes to 0 as delta goes to 0. Because of Besicovitch construction, it cannot be literally greater or equal than 1 because it could because this quantity could go to 0. So we use this greater approximate to denote this meaning. Now, if one can show this discretized Kakeya set conjecture, there is some standard way in geometric measure theory to reduce to use this to prove the Hausdorff dimension version of the Kakeya set conjecture. So now let's discuss why it's difficult to use the assumption that a Kakeya set contains a line segment in every direction. So when we study this kind of problem, we usually use induction on scales. How do we do induction on scales? So now we have a union of delta tubes with one in every delta separated direction. To do induction on scales, we usually intersect the set with some small box. For example, we could intersect the set with this yellow box. Then we will get a set of tube segment. But we hope to say something about the union of those tube segments and then combine the information in each small box to get the information of the Kakeya set. However, the tube segments in the small box do not necessarily satisfy the corresponding Kakeya assumption. So we cannot really apply induction for the union of tube segments in this small box. Even if we take the small box to be a thick tube, there is no guarantee that the thin tubes inside the thick tube should satisfy the Kakeya assumption. So this is the main difficulty, is that if we want to apply induction on scale, then this nice assumption do not preserve under induction or under restricting to a small box. So this assumption is very hard to use. So can we replace it by something else? Let's now think about this question, and we could first consider this more general question. Suppose blackboard T is a set of distinct delta tubes contained in the unit ball. Distinct means that T1 and T2, if they're distinct, if the volume of their intersection is less or equal than 1/2 times the volume of one tube. For example, these two tubes, they are distinct. To require them to be distinct is a very natural assumption, because otherwise we can just keep repeating tubes in the same location. Then one cannot really get a very good bound, a good lower bound here. So the question is, if suppose we have a set of distinct delta tubes contained in the unit ball, how large is the volume of their union? So what is a meaningful lower bound to put here? There are two natural bounds. The first one is the number of tubes times the volume of a single tube. Again, this notation means that it's greater than or equal than delta to the epsilon, and epsilon goes to 0 so let's say greater or equal than delta to epsilon times the minimum of the number of tubes times the volume of a tube, or 1. This is the best possible, because this term means that the tubes are essentially disjoint. Because if they are pairwise disjoint, then the volume of their union equals to the number of tubes times the volume of a single tube. And then this term is also the best possible, because the tubes are contained in the unit ball, so the union is also contained in the unit ball. And then then the volume cannot really be much bigger than the volume of a unit ball. So this means that essentially fill out the unit ball. Now the main question becomes, can we give some criteria on the set of tubes such that we have this very nice bound? The Kakeya set conjecture is like a special case of this question because it asks, is the Kakeya assumption the right criteria? It turns out that to study the Kakeya set in R3, one needs to study this more general like more general, and maybe one can think it's like more difficult question, as we will see later when we talk about the argument. Sometimes it's not necessarily harder to consider a more difficult problem. So now let's look at this question, and we first want to come up with, let's say, some enemy of this question. So here is an abstraction. Let W be a rectangular box containing a unit ball that contains at least one delta tubes. For example, one can think W as A times B times 1 box, where A is greater or equal than delta, and less or equal than B, less or equal than 1. And we take P to be a maximal set of distinct delta tubes in W. Let's say maximal. And then how many tubes are there contained in T? It is roughly the volume of W divided by the volume of T squared. The reason is that there the volume of W divided by the volume of T, many delta separated directions are contained in W. And for each direction, there are the volume of W divided by the volume of T, many parallel delta tubes. So the total number is the number of directions times the number of parallel tubes in each direction. But the volume of their union, since they are all contained in W, is roughly equals to volume of W. So now we try to plug in this example to this inequality. The number of tubes times the volume of one tube is the volume of W divided by the volume of T times the volume of W. And it is much greater than the volume of their union, which is the volume of W, if W is much bigger than T. So this the example fails the inequality by this factor. So this abstraction motivates us to define the following quantity: the density of tubes in T, in W. So the density delta TW is the number of tubes contained in W times the volume of a tube divided by the volume of W. Let's try to digest this definite notation. Now, what is the, for this example, what is the density of T in W? It's since T is contained in W, so the number of tubes equals to the number of tubes contained in W. Now this is square times the volume of T divided by the volume of W equals to exactly W over T. And this also, the density is, in this case, is to what extent the example fails inequality we want to show. So it seems, so a reasonable criteria is the following. We say that a set of tubes satisfies the Katz-Wolff axioms if the density of set of tubes in any box W is bounded by 1. So this means bounded by delta to the minus epsilon. So with this joined with Josh, we proved that if a set of tubes satisfies the Katz-Wolff axioms in R3, then the volume of their union is greater or approximate than the number of tubes times the volume of single tube. In other words, if a set of tubes satisfies this Katz-Wolff axiom, then they are essentially disjoint. Or in some sense, one can rephrase our theorem as follows. For the union of tubes problem in R3, this obstruction is the only obstruction. This Katz-Wolff axiom, this assumption is more general than the Kakeya assumption. In fact, if a set of tubes satisfy the Kakeya assumption, which is this Kakeya assumption is T consists of a delta tube in every delta separated direction, then it also satisfies the Katz-Wolff axioms. So our theorem implies a Kakeya set conjecture in R3. And how to see this? So let's take a W to be A times B times 1 box. And we want to estimate how many tubes are there contained in W. And this is, we only need to estimate how many delta separated directions are there contained in W. And this is the number of delta caps contains in this A times B rectangle on the unit sphere. So this is bounded by AB over delta square, which is W over T. And this implies that the density of T in W is less than 1. So for the rest of the talk, we are going to focus on the ideas that's some of the ideas that go into the proof of this theorem. So before talking about the ideas, let's digress a little and talk about projection theory, because I think a lot of the arguments inspired by recent developments in projection theory. And also, I believe that there is a big tradition in projection theory in Finland. So maybe this introduction is familiar to some of you. So what does projection theory study is, suppose we have a subset of R and E, and we also have collection of, let's say, m-dimensional subspaces, and PV is the orthogonal projection from E to this subspace V. Then we want to say that given a collection lambda of m-dimensional subspaces in Rn, can we find a subspace V in our collection such that the dimension of the orthogonal projection image is large? So here the orthogonal projection image is this yellow point, and then to this subspace is this blue point. We want to show that at least for one subspace, the orthogonal projection has large dimension. There is this classical theorem of Mastron, and I think a higher dimension was proved by Matila, let E be a Borel subset of Rn, then for almost every subspace, m-dimensional subspace V, the Hausdorff dimension of the orthogonal projection of image equals to the minimum of the Hausdorff dimension of E and M. So this is the best possible because this is a Lipschitz map. It cannot really increase the dimension, and also it cannot the dimension of the projection image cannot be more than the dimension of the ambient space. So in fact, if you compare this statement with what we previously our question about union of tubes, then they are quite similar. So this one term is similar to this M, and then this term, essentially disjoint, is also similar to the first term. So you might think now we seem to have a very satisfactory answer to the question because we show that the optimal bound holds for almost every m-dimensional subspace V. But the challenge is that usually we don't have access, or for a lot of the problems, we don't have access to almost every subspace V. We only have access to, let's say, lambda is a lower dimensional subset of the Grassmannian, the collection of m-dimensional subspaces in Rn. And Kakeya set conjecture is a special case where lambda is some special curve. Now I'm going to talk about some of the general strategies people found in the recent years and to study problems in projection theory. So in the space of all sets, like suppose, for example, this be all Borel subsets of Rn, there is special class, it's called sticky sets, where those sticky sets share similar properties at all scales, and it has very rigid structure. The general strategy is that we first study the problem within the special class of sticky sets because it has a rigid structure. So usually the problem becomes slightly easier if we just study it within this class, because it has a lot of structure we could explore. And then once we proved the desired theorem for sticky sets, then we can use it as a base case to do induction and then to prove the theorem for general sets. And this is the technique we use is called the induction scales. So then one of the powerful idea, I think, is due to Parber-Schmerkin, is that we can, for any general sets, we can find some sort of multi-scale decomposition to find some structure in those sets. But for different problems, the sticky sets might mean different things. So it's already non-trivial to identify the right notion of sticky sets for the problem you want to work on. For example, for the Kakeya set problem, we will define what sticky sets means later, but the examples that we have seen so far, this Besikovich construction and the Heisenberg group example, they are both sticky. Also, when we say that it shares rigid structure, it's like the rigid sum product type structure. So this is often a very nice place to apply Bourgain's discretized sum product theorem, which distinguish real numbers and complex numbers. I should say that this similar properties at all scales imply some rigid sum product structure. I learned it from Tao's blog. Also, for some other problems, I learned it from a Thomas paper. So let's look at some theorems proved using this approach. So far, there are not that many, but hopefully in the future there will be more theorems. The first one is I shouldn't say the first one because there are also some other theorems prior to this one that are using similar approach. But for example, the Furstenberg set conjecture in R2. So the sticky case was proved by Thomas opponent and published Merkin. And then the general case was we use the sticky case as a black box to run induction. It's proved by Kevin Ren and myself. Also, the topic of today's lecture, the Kakeya set conjecture in R3 is also proved and use this approach. And there are still many problems that are open and could potentially be studied using this approach. There is the Faulkner distance set problem, where the sticky case was proved by Thomas 9 years ago, but the general case still remains very difficult. And also the higher dimensional Kakeya set problem or even the Furstenberg set problem. Okay, so in the remaining 10 minutes, I hope to talk about how to use this general strategy to study the Kakeya set conjecture in R3. So first of all, it's based on ideas of Katz and Tao that Tao outlined this idea in his blog post. We showed that if the set of tubes is sticky in R3, we will define what it means later, then the volume of their union is greater approximate than the number of tubes times T, then they are essentially disjoint. And then we use this sticky theorem as a base case to prove the theorem for any set of tubes satisfying the Katz-Tau-Wolff axioms. So what is the sticky set for the Kakeya set problem? Here, we say that a set of tubes is sticky if for any row between delta and 1, T row is the set of row tubes covering delta tubes, meaning that for any delta tube in our collection, there exists some row tube in T row, in blackboard T row, such that it contains the delta tube T. So the set of delta tubes is sticky if the T row also satisfies the Katz-Tau-Wolff axiom. So what it means is that the density of the row tubes covering delta tubes is bounded by 1 in any box W. So here are two pictures. So the left-hand side, the set of tubes, it satisfies the Katz-Tau-Wolff axiom, but it does not satisfy Katz-Tau-Wolff axiom at scale rho, so it's not sticky. So why this is the case? Because notice that if a set of tubes satisfies this density bounded by 1, it implies that the number of row tubes is less than rho to the minus 2. Because we might take W equals to the unit ball, and since our set of tubes is contained in the unit ball, I forgot to add this assumption. So using the fact that the density of T row in the unit ball is bounded by 1, one can show that the number of row tubes is less than rho to the minus 2. And so the picture on the left-hand side, there are too many row tubes. So this T row is does not satisfy the Katz-Tau-Wolff axiom. And then the right-hand side is a sticky set of delta tubes. For this row, in fact, it should also be like for every row, the corresponding row tubes satisfies the Katz-Tau-Wolff axiom. It's not concentrated in any smaller box. Also, the picture is can illustrate the word sticky because, as you can see, the delta tubes on the right hand side, they indeed stick with each other. They are very close to each other. A consequence of a sticky set of delta tubes is that it implies that for any row between delta and 1, the corresponding T row, the thickened tubes, and the thin tubes contained in T row, they are all sticky. It means that suppose we have a sticky set of delta tubes, then when we thicken it or when we restrict it to some thick tube, we still have sticky sets. So this is really convenient to apply induction. So previously, we said that one of the difficulties to study the Kakeya set problem is that the Kakeya assumption does not work well under a restriction to smaller box or thickening. But here, the sticky assumption works extremely well on the thickening and restricting to a fat tube. And so it illustrates the advantage of studying only the sticky sets as the first step. So now let's talk about the beginning of the argument. So the setup is, suppose the set of tubes satisfies the Kesta-Wolff axiom, which means for any box, the density is bounded by 1. And for simplicity, let's just assume that the number of tubes is roughly delta to the minus 2. Since we know how to prove the theorem when the set of tubes is sticky, so we might as well assume that it is not sticky. In particular, it should look like the picture on the left-hand side. It's not look like the picture on the right-hand side. So we are looking at some tubes of this shape. Which means there exists some row such that the number of row tubes is much larger than rows to the minus 2. So to do induction scales here, we are going to study the multiplicity of tubes, which is roughly the number of tubes through a typical point in the union of in the Kakeya set. So our goal is to show that the multiplicity is bounded by 1, which is equivalent to say that the volume of union of tubes is greater or approximate than 1. So this is our goal. And now let's look at this picture. So when we say that the multiplicity is the number of tubes through a typical point, so let's look at this yellow point. How many tubes are there through this point? We can see that it's 1, 2, 3, 4, 5, 6. So the multiplicity mu t is 6, at least for this point. And the way we are going to study the multiplicity is we first look at the multiplicity of tubes inside T row, so the number of thin tubes in a row tube passing through this point. So here in this picture, this mu T bracket T row is 2, and there are 2 tubes passing through this yellow point. Since the thin tubes inside T row, they have a very small angle of size at most row. If they intersect, they stay intersect for a little while, and their intersection is, rather than a yellow point or delta ball, is a segment, which we call them grain. It's a segment of length delta over row. So the grain has dimensions delta times delta over row. We call them grains G. Then we decompose the multiplicity of tubes into the multiplicity of thin tubes inside thick tube and the multiplicity of grains. So in this picture, you can see that there are like 3 grains passing through this yellow point. We indeed have this decomposition. This is, after pigeonholing, this is an essentially sharp estimate. So now the challenge becomes how to study the multiplicity of grains. This is a really difficult problem because a priori there's no structure on the set of grains. What do we know about them? So we know that after rescaling, it becomes a set of road tubes. But to estimate the multiplicity, we have no information at all. It could be arbitrary set of road tubes. So what we are going to do is we are going to find some structure in the set of grains and use it to show one of the following. So either the multiplicity of grains is very small and we win, or there exists a small scale such that the set of tubes has a large local density in the, let's say, in the ball of radius tau. And then we can apply some thickening argument to scale tau. So let me just use 1 minute to illustrate how to find structure in an arbitrary set of road tubes. So again, this is inspired by Schmerkin's multi-scale decomposition. So here is the picture. I found it online. Suppose we have a collection of thin tubes, and we want to find structure. So this picture is quite easy to find the structure because we can just find the two boxes that contains them. This is indeed a picture to illustrate. Well, I think one of the key idea is this factoring proposition about finding structure from no structure means that we can find structure from an arbitrary set of road tubes. So we can see that the factoring proposition says that for any set of road tubes contained in the unit ball, we can find a set of blackboard W of some boxes such that the set W itself satisfies the Kastler-Wolff axiom, and then the set of road tubes is very dense inside each box W. So this is a structure that turns out to be very useful to study the union of tubes problem. So the idea is to apply this factoring proposition to our set of grains, and then to find structure within the grains, and then we proceed. We're going to discuss case by case depending on the outcome of the factoring proposition, in particular depending on the dimension of those boxes. So, yeah, I think this summarized one of the key ideas. So I guess I will stop here. Thank you very much.